Yes.
Thank you.
All right, guys, questions on the homework assignments? Questions on the factoring worksheet 1 or factoring worksheet 2? Yes. Questions on either one of the homework sheets before we look at the ones for today? We're good with both worksheets? Now, what we're doing today isn't anything overly different. We're still with factoring, but most of the ones that we're going to look at today, I would consider are special cases. They work out in kind of a unique way. Now, one of them that we're going to cover, you guys did on homework sheet 1. One of the problems is I would consider a special case, but for the most part, they're not any different. So this one here is one of the first ones that we have. So 4x squared minus 4x plus 1. Now, if we look at this one here, the first thing we'll look for is a greatest common factor. Well, there's not one. So we'll do our 2 sets of parentheses with 3 spaces. Now we'll look at the factors, well, our signs first. So we look at the third term. If the third term is positive, the signs are the same and they match the sign of the middle term. So here it's positive and negative, so they're both negative. Now we need to find the factors of the first and third term. Normally we go with the first term, but the third term is kind of nice. It is. So its only factors are 1 and 1. Because whenever I look at these here, I always look for which one has the easiest factors to work with. Only one set. 1 and 1's nice. With 4x squared, well, we know we'll have x and x. Now the factors of 4 are 1 and 4 or 2 and 2. Which one do we want to try first? 2 and 2. And lastly, we check. 2x times negative 1 is negative 2x. Negative 1 times 2x is negative 2x, which gives us a negative 4x. So this is the correct set of factors. Now, you're probably saying, okay, that's not any different. It really isn't any different than what we did the last 2 days. But if you notice, these 2 factors are what? 2x minus 1 and 2x minus 1 squared. So we could leave it as 2x minus 1 times 2x minus 1. You probably, on the first homework assignment, one of the answers was, I think it was b minus 8 times b minus 8. We have the same one. So either one of these will work as the correct answer. They are both the same thing. And the reason this is included in kind of the special cases is this here, 4x squared minus 4x plus 1, is technically a perfect square trinomial, because it can be rewritten as a set of parentheses squared. That's why it's considered a special case. And there are methods or kind of quote-unquote shortcuts for doing these, because all of these come in the form of ax squared plus 2ab 2abx plus b squared, because this would be a squared. Kind of in this form here with x, or we could really say a squared plus 2ab plus b squared is the more correct version, not so much that, is the correct version of how we can look at it and manipulate it that way. Figuring out what a and b are, but I feel it's almost faster or equally as fast to just factor the thing than it is to try to use this formula. Because this ends up being a plus b squared. So, questions on this here? So we can look at one more of these here. and then we'll move on to the next type. And again, with any of the special ones, I'd still be looking for a greatest common factor. It's going to make it easier to work with. And if we look at this one here, 16, 40, 25, well, 16 and 40 do have a greatest common factor, but that doesn't mean anything because 25 does not. So we'll move on to our two sets of parentheses with free spaces. We look at the third term. If the third term is positive, the signs are the same and they match the sign of the middle term. If the third term is negative, the signs are opposite. So here they're going to be the same and they're both going to be negative. Now we need to find the factors of the first and third term. So 16b squared and 25. Well, b squared is going to be b and b. Now we do have several factors for 16, 1 and 16, 2 and 8, 4 and 4. 25 has a few. We have 1 and 25, 5 and 5. So looking at 16 first, which set of factors do we want to try first? So 1 and 16, 2 and 8, or 4 and 4? 4 and 4. Now looking at 25, we have 1 and 25 or 5 and 5? 5 and 5. And if we check this here, negative or 4b times negative 5 is negative 20b. Negative 5 times 4b is negative 20b, which gives us negative 40b. Or we can say that this is 4b minus 5 squared. Questions on these here? We feel pretty comfortable with these perfect square trinomials. I mean, they're not any different than what we've done the past 2 days. It's just they work out to be a single set of parentheses squared, or we can simplify it down to that. We don't have to, but we can if we want to. We ready for the next type? Now, the next type we're going to look at, I believe, are the ones that y'all like the most out of all the ones we had to factor, because these had a special name. They were perfect square, the difference of perfect squares. Because if we look at this here, n squared is a perfect square. It's n times n, something times itself. 25 is a perfect square. It's 5 times 5. And we had the set theorem for a difference of perfect squares. A squared minus b squared is equal to a plus b times a minus b, where a and b are what we would multiply the number by itself or term by itself to get to our original one. So if we're looking at this one here, a would be just n, and b would be what? 5, because 5 squared is 25, n squared is n squared. So if we wanted to put it in the form of a squared minus b squared, we're thinking of this as n squared minus 5 squared. We don't necessarily have to put the parentheses. I put them there mainly for the n squared, because rewriting it in the form of a squared looks the exact same as what we started with. So a is n, b is 5. So we're saying that this is n plus 5 times n minus 5. And I think that's why y'all like these more than the rest, because once we figured out what a and b are, it's one of the easiest ones to do. Questions on number 6? Are you ready for the next one? 16n squared minus 9. Is 16n squared a perfect square? What times itself is 16? What times itself is n squared? What times itself is 9? So we don't necessarily have to rewrite it out in this form for a and b, but it just kind of helps us to say that we have a plus b times a minus b, or in our case, 4n plus 3 times 4n minus 3 is our answer. Questions on these here? I think most of y'all are now remembering why you like the difference of perfect squares over the others. Now with these here, we can have greatest common factors that can pull out. So if we do see one that's two terms being subtracted and a powers to the second, but neither one of them is a perfect square, look for greatest common factors, because it could be we need to pull one out to have it be a difference of perfect squares. Now this one here, y'all probably already have it down as 2m plus 5 times 2m minus 5. So the next one we have is a to the fourth minus 9. So for difference of perfect squares to work, we need both terms to be a perfect square, something times itself. Now 9 is nice, we know that one. That's 3 and 3, yes? So we could rewrite it as minus 3 squared. Now a to the fourth, a squared squared. Because a squared times a squared, whenever we multiply like bases, we add the exponents. Or powers of powers multiply, sorry. Yeah, powers of powers multiply, so 2 times 2 is 4. So a squared times a squared is a to the fourth. So it's still a difference of perfect squares, yes? So here we can say this is a squared plus 3 times a squared minus 3. And we get this here. Now again, whenever we have a power greater than 1, there is a possibility that we could simplify it. But is, looking at either one of these, well, the first one, a squared plus 3 is done. It's not a difference of perfect squares because it's a sum. But if we look at the other one, a squared minus 3, is a squared a perfect square? Yeah, a times a. Is negative 3, or not negative 3, is 3 a perfect square? No. So that's as far as it goes. It's not necessary that it can factor, because we've already seen some that don't factor, even ones that have 3 terms. But when we have a variable to a power greater than 1 and we're factoring, there's a chance that it could. We know for sure that it's done when the power is 1, where we just have a inside one of our sets of parentheses. So questions on this here? K to the fourth minus 36. Well, it's similar to one we just had, because we can think of the k to the fourth as k squared squared. And 36 would be, so this here would be k squared plus 6 times k squared minus 6. For squares, difference of perfect squares, this is as far as it goes, because k squared plus 6 is not a difference. K squared minus 6, well, 6 is not a perfect square. So that's as far as we can take it. Questions on this here? We'll look at one more of these. X to the fourth minus 81. Is x to the fourth a perfect square? Yep. Or x squared squared. 81 is what? So what do we have? X squared plus 9 and x squared minus 9. And the order that we put these doesn't really matter. We could have said x squared minus 9 first and x squared plus 9 second. And as we've seen already, x squared plus 9 is not a difference of perfect squares. That's as far as we can take it. X squared minus 9. Is 9 a perfect square? It's what? 3 times? So what that tells us is that we can take this one step further, because we can factor x squared minus 9. Because x is our a, we'd have plus and minus, and the other number would be? This one? Because this one doesn't factor, because it has to be a difference of perfect squares. Because that's why we can factor it this way, for plus and minus 3. It has to be minus. Yes, and it's more going into if I took x squared minus 9 and solved it, because 3 and 3, because when we solve, looking at this here, we're saying what values of x will make the function be 0. And for x plus 3, it'd be negative 3. For x minus 3, it would be 3. Now we can see that by solving, because the first thing we would do is add 9, telling us x squared is equal to 9. Square root both sides, telling us x is equal to plus or minus 3, which then we could go back to our sets of factors. Now, I'm going to erase this here and do this again, but this time with our other one, x squared plus 9 equals 0. Well, the first step in solving it would be to subtract 9, which is fine. We have x squared equals negative 9. Because when we square root, we would get 3i. It would be different, so it would be x plus 3i times x minus 3i if we were to factor it. But to get there, we almost have to solve it and then go back to the factors. So that's why it doesn't work with plus. The sum of 2 cubes, or sum of 2 squares, doesn't work because of the fact we can't take the square root of a negative. So that's as far as we can take it. Does that kind of make sense? Any questions on these here? Not too bad? Sum and difference of perfect cubes. Now, cubes, we can take the sum of. We can factor the sum of 2 cubes. And we can factor the difference of 2 cubes. And the main reason that this works is kind of going back to the cubed root of negative 1. Because, well, cubed root of negative 1 is negative 1. And we can see that easily because negative 1 times negative 1 times negative 1. Well, negative 1 times negative 1 is positive 1 times negative 1 is negative 1. We can take the odd root of a negative number, we just can't take the even root of it. So that's why we can take the sum of 2 cubes. We can actually factor it out because we don't have the I term coming into play. That's also part of the reason why the quadratic part of it doesn't factor, it has complex terms because of that kind of cubed root, the oddness of it. Now, there was a set pattern for this because once we find out what the cubed version is, a and b, it has a special pattern that works for both of these here. Because in the first one, we do just have a and b, whatever they are. Inside here, we have a squared, a to the first, a to the 0. It's gone. For b, we don't have b, b to the first, and b squared. I got to do this up, down. And it works for both cases with that. The signs also follow a set pattern. It's the same, opposite, always end on a positive note. We match it, flip it, Always end on a positive note. Yep, the dating story we reference once and then don't bring up again. But yeah. So this here, once we see what the cubed root of each is, they're kind of easy to work. So if we look at this here and take the cubed root of x cubed and the cubed root of 125. Now between these two, the cubed root of x to the third is the easier one out of the two. Yeah. The cubed root of x to the third is x. And the cubed root of 125 is 5. In the calculator, you can use second, kind of the arrow key for the TI-30XS. In the graphing calculator, it's math, and you go down. But if you use this A and S, we need to switch to 3. You'll know you have it set up correctly if 3 looks like it's been bumped up, smaller. And here, then we can do 125. So the cubed root of 125 is 5. Now the graphing calculator, if you hit the math button, pull it up here, does have a cubed root option. Math. Because if you notice, the fourth one down is the cubed root. If we want to take the fourth root or higher, we have to use the fifth option. Now we can set this up. So our factors will have 2 sets of parentheses. The first one will have 3. The second one will have 5. Because we'll have 3 signs, 1 in the first set, 2 in the second. And then we'll have our terms. Now for the signs, it's going to be the same, opposite, always end on a positive note. So since it starts out at plus, our first sign is plus. Opposite, minus, always end on a positive note. Plus, minus, plus. Questions on this so far? Now for A, we'll start off with it. In the first set of parentheses, we just have A, or in this case, x, to the first power. Inside the parentheses, our first one, we'll have our first term squared. The middle will be the first term to the first power, or we just write it the first term. And in the last space, it's the first term to the 0 power. We don't need to write it, because anything to the 0 power is almost 1. Anything to the 0 power is 1, except for 0. Except for 0. 0 to the 0 is not 1. It's undefined. Yeah. If we do have time, there is, I know, a video of a mathematician that can explain it better. Yeah. Now, we need to fill in the last part before we're finished, so we need to fill in the second term. In the first set of parentheses, it's just going to be 5. Now, going across the other part, with x squared, it's really 5 to the 0, which is 1. The middle will have 5 to the first, and the last one we will have 5 squared. So the first term is going to 1, we don't include it. The second term, we don't include it, 1, 2. So it's kind of that up and down. The first term is decreasing in power, the second is increasing. Now we can simplify this a little bit, because the x plus 5 in our first set of parentheses really doesn't change. In the second set, we'll have x squared minus 5x plus 25. And that's it there. In dealing with solving, the quadratic part of this will always have complex terms. Questions on this here? We'll look at another one. X cubed minus 64. So to find the values of a and b, we can take the cubed root of x to the third and the cubed root of 64. Now the easier one out of these two is x to the third, because the cubed root of x to the third is x. Whenever the index and the exponent are the same, they simplify out. And later in this semester, we will actually deal with radicals at higher degrees and actually explain, probably for the first time, why that cancels out. It was brought up a little bit in Algebra 1, but we'll kind of go over it again. Now the other one's the cubed root of 64. I only know cubes up to about 5. Yeah. Because I think 6 is actually 316, but not as comfortable with those. To the third, negative to the third, 216. Now, so when we factor this here, we'll look at signs first. So the signs are the same, opposite always end on a positive note. Well, we started off with a, so it's going to be negative, positive, positive. Same, so negative, opposite of that would be positive, and always end on a positive note. So just as a side note, none of the sum or difference of perfect cubes will ever have 3 pluses or 3 minuses. They'll always have 2 pluses and 1 minus, no matter how it's set up. Because either the first set of parentheses is going to have a plus and it's going to end with a plus, or it's going to start with a minus and the next two are both going to be positive. Now we need to look at the first term. Well, we're going to have, let me write the color I want, x, and the bigger one will have x squared, x to the first, and then no x. For our other term, in the first set of parentheses, we'll have 4 in that third space. We won't have anything with x squared, 4, and then 4 squared. And so this will factor to x minus 4 times x squared plus 4x plus 16. Questions on this here? We good with this one here? Are you ready to look at another one? Let's look at this next one here. So this one here is a little bit different because we don't just have a to the third. We have 27a to the third. Now we can still look at the cubed root of 27a to the third and the cubed root of 64. Now the cubed root of 27a to the third is going to have an a, because the cubed root of a to the third is a. We can't type that into the calculator because the calculators, both of them, have to have a value for a variable. But we can still take the cubed root of 27, which is 3. So the cubed root of 27a to the third is 3a. Cubed root of 64 is 4. We already found it once, so we're good there. Parentheses with 3 spaces, parentheses with 5. Now when we look at the signs are the same. Opposite always end on a positive note. Since we start out with a plus, the same would be plus, minus, plus. Now this is here where it seems to be a little different. It's still the same because we can start out with our first term, so 3a. So in the first spot we would have 3a. In the first set of parentheses we'll have 3a squared, 3a to the first, and then no 3a. With our second term, we'll have 4. No 4 is with our 3a squared. The middle we will have 4 to the first, and the last one we will have 4 squared. So really everything except for that middle term in the bigger set of parentheses is similar to what we've done already. Because when we simplify it, well, here we're going to have, 3a plus 4. Just rewriting it back down, that doesn't change. We'll have 3a squared. Well, 3 squared is 9a squared. So we have to square both terms. We can't just square the variable. Now the middle, this is a little bit different because normally we just move the number in front and we're called it good. Here we need to multiply. So 3 times 4 is, and then we have a plus 4 squared is 16. So when our first term has a number with it, the numbers do alter a little bit more than they do when it's not. But that's it. Questions on these here? Let's look at this one here. 192x to the third minus 81y to the third. (192). Let's see if we can take the cubed root of 192. 192 doesn't have a cubed root, but is there a greatest common factor between 192 and 81? Because if we add the digits up, 1 plus 9 is 10, plus 2 is 12. 12 is divisible by 81 is divisible by 3 as well. 9s is the same trick for 3s divisibility-wise. You add them together, and they have to be divisible by 9. 81 is divisible by 9, because we know it's 9 times 9. 192 is not. So all this means is that we're going to factor a 3 out. So this one here is a difference of perfect cubes. It just has a greatest common factor first. So we're going to divide 192 by 3 and get 64. (81) divided by 3 is now, if we do the check this time, cubed root of 64 x to the third, well, we know the cubed root of 64 already is, and we'd have x. Cubed root of cubed root of 27y to the third is going to be 3y. Now, just as a reminder, when we do any factoring and pull out a greatest common factor, it does need to be included in your answer. Now the signs are going to be the same. Opposite always end on a positive note. So since the starting one was minus, for it to be the same, we will have minus. Opposite of that is plus, plus, minus, plus, plus. Our first term that we're plugging in is 4x. So here we'll have 4x. The first one here will be 4x squared. The middle one will be 4x. And then the last one is 4x to the 0, but we don't have to include it. Our second term is 3y. So in the first parentheses, we have 3y. We don't have to put anything with our 4x squared because it's really 3y to the 0, which becomes 1. The middle term is 3y to the first, and our last one is 3y squared. And the last thing we need to do is to simplify this here. So we'll have 3 times 4x minus 3y times, well, 4x squared. 4 squared is 16. And then we have our x squared plus, yes, 12, and it would be xy plus 3 squared is 9, and we have y squared. And what's really interesting is no matter what those two terms are, as long as they're perfect squares, it works.
So the two hardy functions, x and y is the same number.
Because x and y is really any number, they're just standing in as a variable. But as long as whatever this term is a perfect square with addition or subtraction of another term that is a perfect square, this method always works. We'll always be able to factor it this way, which is kind of nice. It's really interesting that it does work this way every time, no matter what we have. But the note sheets aren't done. We're going to stop here and finish tomorrow with grouping. Factoring by grouping. It's not going to take the whole time, so you will have time to finish up the homework sheet and or the other two.